effect. And this brings me, I think, nicely to the next piece of our core tech that I'd like to talk about, which is our Cairo language. It's a language for causal probabilistic programming. So maybe this feels like a little bit of a leap. Why is this connected to the stuff that I've been talking about with Mara? But we think that the needs of the Mara agent are actually very well satisfied by probabilistic programs, and in particular by probabilistic programs that we can ask causal questions of. So we can think of a probabilistic program as a pretty good representation of a world model, as a way to predict what might happen next in a world. And by using probabilistic programming, we can do all of the things that I said that we wanted to be able to do with these agents. We can make predictions under uncertainty. We treat our world model maybe as not just a single model, but as a model that is non-deterministic over multiple possible submodels. We can perform inference to learn things about latent variables present in our description of the world. And by using Cairo, we can actually also make a whole bunch of causal queries on these models. So we can perform interventions in Perl style. We can compute counterfactuals, and we can compute causal explanations. So just to give you a little flavor of Cairo, Cairo is our causal probabilistic programming language. It's built on top of the Pyro PPL, if you're familiar with Pyro. And so one of the nice things about doing that is that if you have a bunch of Pyro models, you can actually bring them wholesale, and you can start to ask causal questions about them with our stuff. So they slot right in. But what's going on here is we have a little model, and it's drawing some samples from some normal distributions, and those normal distributions parameters depend on the previous samples that we drew. And so I said earlier that we can do stuff like perform interventions on these models. And so what does that look like? And I want to talk about a little bit about how we implement some of these causal features, some of this stuff like interventions. And the way that we do that is we treat a lot of the internal machinery of Cairo programs as algebraic effects. And we use algebraic effects and handlers to implement a lot of these causal queries. So this sample here, this is actually an effect. We can override that effect later. And that brings me to the next piece of technology I want to tell you about, which is a library called Effectful that we've been working on this fall. It's a way to do algebraic effects in Python that we found to be quite powerful, and we've been working on integrating it into Cairo. So just a little refresher, what are algebraic effects? They're used for lots of things, lots of contexts. People have been exploring them as a way to describe things like concurrency and I/O. But we're really more interested in them as a way to talk about semantics, and a way to talk about semantics in particular that are dynamically bound. So we have these models, which we represent as programs. We want to change the behavior of those models, maybe in different contexts, to do things like inference. So we represent large parts of the internals of those models as effects. And then by adding handlers that wrap around them, we can change their semantics and get interesting and useful behavior out of them. OK. So, for example, what if we want to perform a Perl-style intervention on the variable x? Well, in Cairo, we can do that by wrapping the model in an effect handler. The effect handler here is called do, and it says that instead of doing whatever x was originally, we're going to replace it with some intervention value. And so wrapping this model in this handler is actually equivalent to a program transformation. We take the original program and we modify it so that instead of sampling, we sample and then we pass the sample into a function called intervene that by default returns x prime 5 minutes left. So by default, this intervene function is just going to return the interventional value. And so we get an intervene model. But we can actually do even more than that because intervene is itself an effect. And so we can override it. One way that we might want to override it is to compute counterfactuals. So if we'd like to intervene and then think about not just the intervened world, but also the factual world, we can do that by applying another effect handler called multi-world counterfactual that replaces that intervene effect with something that, instead of returning the interventional value, returns both values and continues threading both values through the rest of the model. So what we get now is a counterfactual program that when we sample from it, we get values from both the real world, the model world, and the intervened world, and we can compare those values directly because they share randomness in all the places where we didn't intervene. So hopefully what I've done is convinced you that programming languages are particularly powerful tool for building the kinds of AI applications that we're interested in building. We're using program synthesis in the Mara project. We're using causal PPLs and Cairo as part of Mara and as part of a lot of our other projects. And we're using algebraic effects as a way to implement these causal PPLs in a particularly composable way. And so if any of that sounds exciting to you, hopefully some of it does, you're all programming languages people, we're hiring, and we'd love for you to come work for us. We're hiring at research scientist, research engineer, postdoc, and intern level. So if any of this sounds like the kind of stuff you'd like to do, come talk to us and we'll tell you about all the other stuff we're doing. And I'd also like to plug our social event tonight. So please join us. You RSVP at this link. It's also on the LAFI website. I have a bunch of t-shirts like this, so if you'd like to look like me, I've got t-shirts in the back that you can come grab. All right, thanks very much, and I'd be happy to take any questions.
Thanks very much. Jack. We have about 3 minutes for questions, and in the meantime, could other Jack come set up?
Okay, so what's the difference, like, briefly between an observer and a do?
You're asking the deep questions.
Okay.
So do basically goes into the model and changes it. Observe you can think of as affecting your latent variables. I'm hoping I'm getting all of the details right here. But basically, observe says I have maybe some latence in my model, and I've observed something, and that's constraining the latence in some way. Do is saying I want to take my model and I want to kick it out entirely. I'd like to create a new one where this happened instead.
They're kind of similar, but
they are similar, but they're different.
Okay. All right. Yeah, right.
Is that helpful?
I think we don't have too much time. It's example.
Fair enough. Other questions? Yes.
Yeah. So I'll just shout. So. Oh.
Hello? Okay.
No more shouting. Okay. Hi. This seems really cool. I really like how you've used algebraic effects to cleanly capture conditioning, intervening, and so on. My concern is performance, right? So have you found that this is a reasonably performant way of implementing these things, or have you had to spend significant effort optimizing these particular kinds of effects? I'm just curious what's
That's a great question. And the answer is that a lot of these effects stage away. So largely we're generating PyTorch code, and so we can. Right now we're fighting the PyTorch compiler, and it's often winning. But in a world where the PyTorch compiler was a little bit better, or where we moved some of this technology over to something like DAX, you would be able to stage away basically all of the effects